Good afternoon, everyone, and welcome to the fourth and final Distinguished Faculty Lecture of this academic year. I'm Joel Martin, and it's my privilege to serve as Vice Provost for Academic Personnel and Dean of the Faculty. And I say it's my privilege to serve in this capacity because it's in my job here, there's not a day that goes by that I don't learn something really incredible about the work that our faculty is doing, and I'm always inspired to learn what our faculty are doing. We have a great faculty doing important work and creative work, and this series celebrates the success of that faculty. Since the conception of this lecture series, we have recognized more than 150 of our esteemed and accomplished faculty members. That happens to be a nice number considering that we're entering our sesquicentennial, celebrating 150 years of outstanding teaching, research, and service. I'm also happy to note that not once in 150 plus lectures that have been given in this series has the cell phone or iPad of any audience member ever dinged or donged during the lecture. Not once, never, and that reminds me. I would now like to take this opportunity to recognize and thank the work of our selection committee. Given the great high quality of our faculty, theirs was not an easy task to select only 4 speakers this year. Wybon Gong, Department of Electrical and Computer Engineering, Jerice Hansen, Department of Communication, Manisha Sinal, Department of Afro-American Studies, and Michael Williams, Department of Geosciences, served on the committee. Please join me in thanking them for their service. This afternoon, Professor Laurie Brown will present her lecture entitled Magnetic Field Reversals, the Ups and Downs of Earth's Dipole as Seen from South America. While studying an active volcano in the Chilean Andes, Professor Brown discovered lava flows that gave evidence of the most recent reversal of Earth's magnetic poles. Professor Brown will discuss how her findings will help predict with greater accuracy reversal processes and how future reversals may affect human activity. Professor Brown started her academic career at Middlebury College with a degree in mathematics. An elective geology course in her senior year at Middlebury revealed to her the field to which she would devote her lifelong passion and research. After earning a master's degree in geophysics from the University of Wyoming, she pursued studies in oceanography and earned her doctorate from Oregon State University. Professor Brown joined the department here of Geosciences and Geography in 1974 and has been an active member of the campus community since. She has served as interim head and associate head of the Department of Geosciences and currently serves as the graduate director of Geosciences. Professor Brown has also served as a visiting professor at the University of Wyoming and New Mexico Institute of Mining Technology. She was recognized as a Fulbright Scholar in 2000, focusing her research on the Norwegian Geological Survey. Professor Brown has also spent time as a summer faculty fellow at the Jet Propulsion Laboratory at the California Institute of Technology. She was also awarded the Outstanding Educator Award by the Association for Women Scientists. We're delighted to have Professor Brown here to speak with us today, and I would now like to ask her dean, Stephen Goodwin, to the podium to introduce our distinguished lecturer. Thank you.
Well, it is certainly a distinct pleasure to be able to introduce Laurie Brown to you today. Laurie studies paleomagnetism. That's the geologic record of the Earth's magnetic field as captured by rocks. Now, rocks are a kind of good thing in the sense that they stay around, right? Maybe they get modified a little bit, they get heated up a little, they get deformed a little bit, and maybe it makes the interpretation a little bit more complicated, but rocks tend to stay around. And so Laurie's been looking at how the Earth's magnetic field has functioned through geologic time. Now, this field has a tendency to flip back and forth about 180 degrees in orientation. And when I was in Geology 100, they said, well, we don't really know why it's flipping around, and it seems to be kind of random. And so hopefully Laurie can help me a little bit, catch up with what's been going on in the last 30 years in paleomagnetism. I can learn a little bit from all of this. Because Laurie has been studying the reversal of magnetic fields for most of her career, including what happens to the field during the reversal and also how fast the reversals occur. Now, Laurie's truly a distinguished scholar, and Joel just told you some of the accomplishments that she's had over time. But in addition to being highly respected by her colleagues for her scientific achievements, Laurie is especially appreciated for her dedication and for her devotion to the department, to the university, and to her discipline. From a dean's perspective, she's pretty much the perfect faculty member. One of the nice things about this distinguished lecture series is that we get to see multiple sides of faculty members that we've known for a long time. And as department head Mark Leckie points out, he says, Laurie has certainly been a pioneer. When Laurie joined the faculty at the University of Massachusetts in 1974, less than 14% of the faculty were women. Today, that number is up to 37% of the tenure system faculty being women. And I'm very proud to say in the Department of Geosciences, it's 42%, a very impressive number, and a very impressive department, one of the most collegial departments on the campus, certainly would say. Now, to try to give you a little sense of the impact that Laurie's had, I'd like to quote from two former graduate students. And both of them traveled here to be with Laurie today, and I think that certainly speaks volumes to the kind of mentor that Laurie was. The first is Dr. Suzanne McEnroe. Susan, give a little wave. Here's what Susan had to say. There are many outstanding scientists in the U.S. What distinguishes Laurie from this distinct group is her contribution to the development of women scientists in geology and geosciences, and geophysics. Both geology and geophysics are still highly male-dominated disciplines. Geophysics today has less than 20% women in senior positions. This number would be much lower without Professor Brown's outstanding teaching and mentoring throughout her career. She also engaged many women students in her state-of-the-art research projects. With Laurie, one could equally end up on top of a mountain in Chile, sampling a volcano in Hawaii, or in the Arctic tundra in Norway. Laurie Brown has been a strong mentoring presence in the lives of women geoscientists, both at the University of Massachusetts and through the wider geosciences community in the U.S. and internationally. She has worked continually and selflessly to promote women in science. And Dr. Suzanne Solianis, who's also with us today, had this to say. Laurie was more than an advisor and a mentor to me. She was an inspiration. She was a pioneer as a female geophysicist when she came to UMass and has persisted as a pioneer throughout her career. She works in some of the most challenging physical areas in the world in pursuit of her research. She has a rich and warm family life. She has a wide circle of devoted friends. All of this, and she's a dedicated teacher. No one could be a better example of a fully rounded professional. She is an inspiration to women and to all scientists. And I would add, she's an inspiration to all of us here at the University of Massachusetts. So I'm very much looking forward to hearing Dr. Brown today tell us about magnetic field reversals, the ups and downs of Earth dipole as seen from South America. Ladies and gentlemen, Dr. Laurie Brown.
Thank you, Joel and Steve, for those very, very nice introductions and the very lovely words said by my former grad students, neither of whom I paid off for this. I'd also like to thank the committee for giving me this opportunity to talk to you today about a subject that's really dear and near to my heart, magnetic field reversals. So I'm going to start first with a little bit of just the outline, give you an idea where we're going. I'm going to describe a little bit about the magnetic field, and then we'll get into this field of paleomagnetism, called paleomagic by some of my cohorts. We'll look at reversals of the magnetic field, and then finally, or hopefully pretty soon, we'll get to go down into the Chilean Andes and sort of see how we try to investigate one of these magnetic field reversals. And then finally, at the end, I'll get to this idea of when is the next reversal going to be, and do we need to worry about that? So as most of you are well aware, the Earth has a magnetic field. It's not really very strong compared to the magnetic field of a magnet on your refrigerator, but it's certainly one which we can measure, and it will interact with your compass, if people had compasses anymore now that we all have GPS systems. But the interesting thing about this field is it looks quite simple on the surface. It looks like we have a large dipole, say, or a big bar magnet in the center of the Earth with a pole at the north and a pole at the south. Well, what I want to do first is just look a little bit at some of the historical background we have of the magnetic field and the people who were important in sort of figuring out the things that we know now. And I'm not going to go through this in great detail, but I'm going to talk about a couple of people, and eventually in this talk you'll see why I picked the people that I did. And the first person I'll mention is William Gilbert. Gilbert was a physician in London back at the end of the 16th century. He actually eventually became physician to Queen Elizabeth. And although he earned his living as a medical doctor, his avocation was geomagnetism. And he wrote a huge treatise, or a tome. It was actually 6 books on magnetism, called De Magnete. Of course, it was all in Latin. It had 115 chapters, and I haven't read it myself, but I've been told that their paragraphs are pages long in it. But many historians of science consider this to be sort of the first real textbook in the sciences. It was not just recording observations and then maybe some conclusions from them, but he put in this all the work, all the information he could find on the magnetic field at that time, and as well as his own ideas. And the big important thing about this work was that the conclusion he came to was that the magnetic field, which people were aware of at that time, was internal to the Earth. It wasn't something just floating around in the atmosphere or coming from the heavens above, that it was produced in the Earth. And the second person that I'll talk about, just briefly, is Carl Friedrich Gauss. Many of you, I'm sure, know of, a very famous mathematician about 200 years after Gilbert. He also, besides doing a lot of very interesting mathematics, had a very personal interest in magnetism. And he actually set up a magnetic observatory of his own where he could measure the aspects of the magnetic field. And he encouraged these observatories to be set up in other places of the world. He also developed a method to determine intensity of the magnetic field, which up until that time people had not been able to measure easily. And then he took spherical harmonics, which were just being developed at that time mathematically, and applied them to the magnetic field, which allowed us to have a rather long and complicated but unique description, mathematical description of the magnetic field. And we still use the solution that he came up with, the mathematics he used. You need to have data points to calculate the coefficients, and which we now use from satellites. He used them from these observatories he set up. And we now refer to the coefficients in this equation as the Gaussian coefficients. So if we look at the present field now, we know a lot about it. But you'll notice here, the field is not quite aligned on the rotation axis. It's off by a couple of degrees, 11.5 right now. We can measure this field easily. We have a field magnetometer in the Geosciences department. We can walk around campus and measure the magnetic field. You can measure it from ships, from canoes, from boats. You can drag them beneath helicopters. You can attach them to airplanes, and we have satellites that are just measuring the magnetic field. So we have lots and lots of information about this field as it looks on the surface of the Earth now. And we know that just over human timescales, this field can vary in terms of its absolute direction and its intensity. We can describe this field by vectors. And the easiest way to look at these are these little vector lines here. The length of the vector gives the intensity of the field, and the direction it points tells us whether it's pointing in or out. We can then use angles to determine and describe these magnetic vectors. You'll notice the vectors around the equator are short and just about horizontal. The vectors near the poles are much longer. The field is twice as strong in the polar regions, and they point either directly out or directly in to the field. So we can then describe the magnetic field vector, shown here in red, by using its declination, that is its angle it is away from geographic north, and its inclination, whether it's pointing up or down. And by convention, in the northern hemisphere, the vectors are pointing down. And because all of this work was developed in northern hemisphere institutions, we consider that to be positive. And in the southern hemisphere, the vectors are pointing up out of the ground, and those inclinations we consider to be negative. And we'll use this same terminology, inclination, declination, intensity, when we get to look at the paleomagnetic field. So just for a brief moment, I'm going to talk about the source of the magnetic field. This could be a whole lecture in itself, but not given by me, because I'm not an expert on the source of the magnetic field. Both Gauss and Gilbert told us that it was internal. They thought it was inside the present Earth. What we know about it now is if we take a little slice out of the Earth and look at it, so here's a section of the Earth with the inner core down at the center, which is solid, then the outer core, which is liquid material, mostly made up of iron particles, and then we have the solid mantle, and finally the Earth's crust and surface where we are up here. We know that the source of the field is down here in this liquid core where we have charged particles. The connection between electric currents and magnetic fields, of course, is known by anyone who's taken even basic physics. And we have various motions within this outer core that produce the magnetic field. The Earth is rotating, so we have some rotational motions, but those alone would not be enough. What we also have are some currents here set up because we've got a hot inner core and a cooler mantle above, and we have some transfer of energy going. And once this kind of field gets going, we refer to this as a geodynamo, and once this field gets going, it will perpetuate itself. So if you have the initial field to start it, then it can just keep going. People tried to model this, and in recent years they've had some luck. They use the 10 equations of hydromagnetodynamics to do this, and you have to make a lot of assumptions. But then using Cray computers, they can come up with a model of what the field might look like. Here, blue is going down into the body here, and yellow is coming out. So we can make models and show that this works. All right, so we know a lot about the present field. We have a bit of an idea of where the field comes from. But now what I'm interested in is the idea that the Earth has had a field probably for a very long time, and can we catch that? Can we measure that field that's been around? And a couple of people who have been influential in that, oh dear, here we're going crazy. All right, we'll stop right here. Bernard Brunies is the first person I'd like to talk about. He was a Frenchman in the beginning of the 20th century. He was a mathematician and a physicist working in a university in central France where they had these beautiful, young, 6-million-year-old volcanoes. And he noticed there that some of these rocks would attract a magnet and be magnetized in the same direction, and some of these volcanoes repelled the magnet and had an opposite direction. He published a small paper on it in 1906, just a couple of pages, observational thing, and then he never really did anything else with it. About 20 years later, across the world in Japan, Matsuyama was studying, sort of doing the same thing with lava flows, but he measured a lot more, and he found that all the lava flows that were on the surface and were the really young ones all seemed to have directions similar to the present field. But if he looked at older lava flows that seemed to be down below, they had reverse directions. And he published this in 1929. Well, we all know what happened in 1929, and there was not much science done for about 20, 25 years. And it wasn't until the 1950s and into the 60s that some of these ideas that were developed at this time then came to fruition. And we developed this field of paleomagnetism. The idea here is that certain minerals, particularly iron oxides, our friends magnetite and hematite, have the ability to to lock in a magnetic field when they get formed. And this is what we call a permanent or remnant magnetization. So when the Earth's field is removed, these rocks are still magnetized, and the vector, the magnetization it has, is parallel to the field when they were formed. And this magnetization can be measured in the laboratory millions and even billions of years after the rock was formed. So we can collect a billion-year-old rock, which Suzanne and I have done in the Adirondacks, and we can bring it back and measure the magnetic field that was recorded at that time. To sort of see how this works, at least in volcanic rocks, we need a volcano. So here's Pu'u'o on the big island of Hawaii, erupting in 1986. And you can see, so we've got hot molten material, and it's flowing down and hardening into this black lava. And essentially what's happening, think about here's Pu'u'o erupting. It's happening in the Earth's present magnetic field. When the material is very hot, say above 600 degrees, it's just all the mineral grains are there. But as it begins to cool, the magnetite grains, when it gets to a certain temperature here, the Curie temperature, and for magnetite this is about 580 degrees, the magnetic direction becomes locked in these grains parallel to the magnetic field. And most lava flows have maybe 2 to 5% magnetite in them, so they have enough so that when the magnetite gets cooled, we have a rock that's carrying a signature. So then, what you need to do to study this is you have to go and collect these rocks. And so we drill and orient rocks in the field. We can then measure this magnetization in the laboratory. And we have to perform numerous tests on the stability, the reliability, the relative age. We do rock magnetic studies to make sure everything that we have is proper and correct. So what people found out, and then you came into some rocks that were reversed, shown by the blue arrow, and then you came into something else that was normal. And they realized that there was a stratigraphy here, so that these were the oldest rocks, and these were the youngest rocks, but the field had changed polarity by about 180 degrees. If you could date this lava flow here and this lava flow here, then you'd know that in between, the field must have reversed. And this allowed them to start setting up a time scale of the reversals. And this is one of the first time scales that Alan Cox and Dick Dole at the USGS developed in the 1960s. And this goes from 0 to 5 million years. And the black periods are when the field was normal. So the time we're in right now with a normal field goes back to 0.78 million years. And the first researchers doing this started naming these, what they called crons. And the first one they named Bruni's. And the second one they named Matsuyama. The third one was Gauss, and the fourth was Gilbert. So you can see why I picked those 4 guys. They're dear to any of us who do paleomagnetism. So the reversal here from the Matsuyama period, which is mostly reversed, although there are a few little times when the field flips back and forth, this would be the reversal here from Matsuyama to Bruni's, and that would be the most recent one. At the same time that Alan Cox and Dick Dole were doing this kind of work, they collaborated with a fellow named Dalrymple, who was at Berkeley at the time and was developing one of the first potassium-argon labs where you could use radiometric material to date rocks. And he started dating these same rocks, so he was able to help put dates on things here. The problem is when you get back about 5 million years, the error bars on the dates are larger than some of these short little events. So they could no longer sort of discern all the variations in the field. But at about that same time, something else very fortuitous happened. This was the 1960s. Plate tectonics was just being developed. And what they found in plate tectonics is that the seafloor is a beautiful tape recorder for magnetic field reversals. And if you know anything about plate tectonics, you know that we make new material. We have spreading centers, most of which are in the oceans. As new material wells up, it cools down and gets magnetized in the field when it erupts. it then moves away across the ocean as new material comes in below it, and that material gets magnetized in whatever the field is then. So it leaves a record on the seafloor of these periods of normal and reversed. And this diagram goes from 0 up here all the way down to 50, 60, 110, all the way over to 160 million years ago, which is the oldest ocean floor we have. What you can see is we have lots of reversals, although every once in a while the field gets sort of stuck. And we have this one period here, Cretaceous quiet zone we call it, where for about 30 million years the field stays in normal polarity. Okay, so we've well established the fact that field reverses a lot. We've established that we have this method of paleomagnetism to look at things. And then we say, well, what do we do with all of this? So I've been here 38 years. What have I been doing all that time? Well, there are lots of things you can do with it. You can correlate different rocks in units. You can do relative dating, particularly in deep sea sediments. They do this where they aren't able to date in other ways. You can investigate structures like folding and faulting. You can look at the position of the continents in the past. Decide where was North America a billion years ago. You can do latitudinal locations because that inclination of the magnetic field is related to latitude. So we could go out to the Holyoke Range here, down in the notch. We could collect a sample, bring it back to my lab and measure it. We would find that its inclination is about 20 degrees, and that this part of North America was about 15, 20 degrees north of the equator when the dinosaurs lived here. So a very different climate than we have today. And then finally, you could investigate, say, the field over time, looking at how it varies, paleosecular variation. But what I really want to talk about today is this idea that we have these two normal and reversed periods, but what is happening in between? How do you go from one to the other? And can we find information in the geologic record that helps us figure out what is going on here? So first, let's sort of review what we sort of know about reversals up till now. They occur really frequently in the geologic record. In recent time, we have about 3 reversals per every million years. But there's no pattern to it. It's not like it works steadily one way or the other. The time for a reversal must be really short, because as you'll see in a few minutes, there are almost no records that occur right during the reversal. There is some evidence, particularly from sediments, that the field decreases in intensity before the reversal and stays low during the reversal process. And then finally, there's been some suggestion that maybe there are preferred paths when the field flips or changes position that would follow longitudinal directions and sort of stay in the same place. And I showed you before that sort of what we call the spaghetti diagram, the theoretical models that have been done. And if they let their models just run and the equations unfold, they find that the field does just reverse as part of the unfolding of the equations. You don't have to do something specific. You don't have to shock the Earth or have a big change or something like that. Reversals, the field is just as happy normal as it is reversed, and very small things seem to trigger it. Okay, so I'm a field paleomagnetist, so my idea is that you go out and you find some place where you can measure these reversals. So what do we need? We need a volcano that's just the right age. So you need a volcano that came out during one of those reversal times. This is hard to deal with because although we have lots of ages of different rocks and we can date rocks, it has to be really, really accurate because you've already gotten the idea the reversal is going to be pretty short. So finding the exact right age is difficult. We also need enough exposure so we can sample it. Now here's a beautiful volcano. This is Villarrica down in southern Chile. Sort of a classic volcano. It's actually smoking a little bit because it's an active volcano. But what happens when this volcano erupts is the lava flows down its classical cone shape. And of course, what happens then is the outside of that volcano is covered with young lava flows. And you have no access to the older flows, which are deep inside the volcano. So it really turns out that looking for a reversal is like looking for a needle in a haystack. And any of us who have spent any time dealing with funding agencies know that they don't like to, and they certainly will not, pay you to go and just look for things. If you find this needle, they'll pay you to go and study it in great detail. So what you need is you need a lot of luck. You have to run across one of these reversals and find it, and then you can go and ask for money to study it. So that's what happened to me. I was involved with a group that wanted to study a big volcano on Earth, mostly from the geochemistry and the petrology point of view. And so where we went was to South America, because oh dear, we went very fast. We went to South America because the Andes are all a whole line of active volcanoes. And this is because they're on the edge of the South American plate, and the Pacific Ocean here in the Nazca plate is being subducted down below that region, forming continuous volcanoes. And the one we went to here is called Tatara San Pedro. If a little cartoon here just to sort of show you what's happening in a subduction zone. So here's the oceanic plate, and it's being subducted down underneath. Here's South America, the continental plate. As this cold ocean lithosphere, but it's wet, goes down, it begins to melt and forms magma, which then comes back to the surface as these volcanoes. So here's the volcano we went to. You can see it looks nothing like classic Villarrica. It's a volcano with large erosional features on it, but it means you can see down into the equation. And for this, I have to say thank you, glaciers, because it's the glaciers the glaciation that was on this volcano 20,000 years ago and earlier that left these deep ravines that allow us to sample these things. So as I said, we went to look at this volcano. I was the only paleomag person. I went with a number of geochemists, including Mike Rhodes from this university, and some petrologists and some geochronologists. And we were going to totally take apart this volcano because we could sample it all the way around. And the paleomagnetism was going to be used to help correlate from different parts of the volcano. There have been a few young volcanoes, young lava flows. This is a lava flow after the glaciers left, and it's filling that valley. But luckily, this volcano wasn't really active the last 20,000 years, so it hasn't covered up all these deep sections that we want to study. There were no geologic maps of this area, so we made one, a crude one in the field, and all the colored areas here refer to the volcanic units, with the yellows being sediments in the river valleys. This map is about 25 kilometers wide and about 30 kilometers long. There are no roads shown on this because there are no roads. The closest road will be over on the far wall there. So it's a place where you have to either pack into, or sometimes we used horses to get in here and move around. But we just want to look at one small area of it, and that is along this Quebrada Turbia section right here. The first year we went down there, we spent 3 months, and we had about 10 or 12 people in the field, and we did a lot of work, collected a lot of samples. And we all agreed at the end of that 3 months that we were going to take our samples from this section right here. What we did is we sampled every single lava flow, and we collected samples for the geochemistry, the petrology, the paleomagnetism, and the geochronology. And we'd take this section, and we'd all work on that first. And then there was going to be a meeting of the American Geophysical Union in a few months, and we'd all present on the same rocks. Well, we took our cores home, and my grad student, Jim Pickens, who was working on this project, and I started measuring, and we started at the bottom, and the first one came out. That was a little odd looking. The second lava we measured, that was odd too. Then the next 10 lavas were really strange. And so I'd never worked in South America before, and I thought, was I holding the compass upside down? You know, did I do something really odd? Part of the problem was we had assumed that this volcano was young. And by young, I mean we thought it was less than 500,000 years old. We thought it all should have the same magnetic direction closely. But what we realized as we sat there and looked at that data really soon was what we had were 2 flows on the bottom that were reversed, and then we had 10 flows with a really strange direction, which we call transitional, and then above that we had the normal flows. So we realized right away we had found the Bruns-Matsuyama reversal. I'm going to show you just a little bit about doing field work in the Andes and Paleomag. This is one of the ways that many of us get into this field of geosciences, is because we love being outdoors and doing this kind of work. So this is the valleys on the way into, hiking into this part of the, to the volcano. It's quite lush and nice, but once you get into where we work, these are the sections we're going to drill up here. This is the water supply and the only flat ground, so that's where we hang out during the evenings. Although some years we used horses, we found that actually it was far more efficient to carry everything we needed ourselves. But this meant I had to carry the rock. We had to carry the rock drill, the gasoline, the food, the camping gear, etc., in for several weeks in there. And this is Jim Pickens, who was the PhD student who worked on this project. And I've spent about 6 months total down in this area, part of Chile, working, and all that time it only rained twice. So we very early on gave up tents because they're heavy to have to carry them along. So this was our campsite where we spent several weeks while we were sampling this section. You just sort of lay down on the rocks that were a little bit smaller than the rest of them, and had your gear and stuff around there. Luckily, this part of Chile has no wild animals that bothered us. The only thing you ever saw were condors, which would fly over pretty low and sort of figure out could they lift you up and take you off or not, but they decided we were all a little too heavy. So you could just leave all your stuff around and it wasn't a problem. So we drill in the field, and what I use is a chainsaw engine that you just take the chainsaw off and give to your friends, and then you put on it a diamond bit to drill. We drill cores that are about 1 inch in diameter and several inches long, but you need water for it, and you need about 3 or 4 gallons of water to do one site. So here are my grad students and one undergrad who are with us 1 year there working. We need the water for drilling. Then you have to orient the cores because you need to know their relationship to where they are in space. You can't just pick up any old rock and bring it back. You need to know how it's sitting in space. So we orient the cores. And then also we're dealing with statistics. We don't just take 1 sample per flow and measure it. We take 5 to 10 samples and you measure them all and then average them together with special statistics that we use to get good information. And then we would do 1 site per lava flow. And as I said, the big deal is the water. So here's Jim actually watching Lynn, who was an undergrad, as she drills. But there's the water down there. That's the stream you saw Jim marching through. So it's quite a long ways to get the water up there. So actually when we did field work, you spent 80% of your time carrying the water up and down, and you spent about 20% of your time actually collecting data. Okay, so let's look at what we're looking at. So this is that west wall of Quebrada Turbia, where we started the first year, and we did a section in right here, and there are 48 lava flows there. This wall is about 1 kilometer high. And so the first section we did that we found so interesting was right here. And on the bottom there was this big fat thing that was quite old, we found out later. And then these are the flows that are transitional, and then you get up and above into these other flows. So in the bottom of this section there's an ash layer, and the ash layers usually indicate that some time has gone on. So that soil has developed and time has passed between the unit down below this and this flow 2, which was the beginning of the section. Here's Jim at the base of flow 3. He's just sampled there. We then climb up through flow 3 and find flow 4 up on the top somewhere, hopefully. And the section that we had here included 12 flows. That old fat thing down at the bottom, which is almost 1 million years old, then an ash layer. Then we had these 10 flows that were transitional, another ash layer, and then a much younger flow. So that's what we came home with the first year, and we're absolutely ecstatic. But we then realized, as we measured these in the lab and looked at the situation, that this package of flows you could trace down the valley, and there were a whole lot more of them down here. So this is when NSF was like very helpful about funding. This was a given. They knew we knew there was a reversal there. We knew there were more rocks there, so they said, yeah, go back. So we've gone back several times to sample the rest of this. So this is, we call QT11 here. This section right here, it sits on what geologists call basement. That means any rock older than the ones you're interested in. So these are the rocks that were there before this volcano was built up. So these are older rocks that we're not interested in. But again, at the base here, here's the lowest flow. There was an ash layer below it. Basement is off down here. So we sampled up through this section. And here we found 22 flows altogether. This is looking from across the valley at it. So we found the first 17 flows all had the transitional directions. And then we found 3 flows that were normal. And then there's a break. And the top 2 flows have different chemistry and are much younger. So we had another nice big section here. So now I'll have to show you a little bit of data. And some of this I'll just explain briefly. Different studies we can do to find out things about our rocks. One of these is we can find what temperature it is that the rock loses its magnetization. And so this is a study where on the vertical axis here we're measuring magnetic susceptibility against temperature, and we start at 0 and we go all the way up to 700 degrees centigrade. And you can see it's got some magnetization until it gets up here above 500 and then falls way off. So that by 600 there's no magnetization left. You can cool that same sample down and it gets its magnetization back. This point where this happens, this temperature, tells us the mineralogy. So in this case, this is a hematite. Over here on this plot, we're just plotting measurements here that we take on hysteresis. That is, how does this sample respond to being put in different magnetic fields? The important thing about this diagram is the labeled areas here are divided by the grain sizes. So MD is multi-domain, big grains. These are little tiny grains. These are sort of just the right size grains. These are the pseudo-single domain grains that have the most stable remnants, and they're the best able to hold the magnetization. So this is where you want your data to fall, and that's what we see for the data from Totara San Pedro. Another thing we can do is measure how strong these samples were when we brought them back from the field. And so here, we're just plotting against the number, the flow numbers from the bottom of the section to the top. And then here we're plotting the intensity when we first measured them. And you can see the blue are all the transitional ones. They're all very low. They're all less than 1 amp meter, whereas the reverse samples and the normal samples are much stronger. So these were relatively weak compared to the normal and reverse samples. We also want to look at the stability of them, and I'm not going to go into the details of these diagrams. Vector endpoint diagrams, essentially what we do is we take one sample, and we slowly peel away the magnetization and sort of see, does it save its own direction? Does it stay pretty good? And these indicate as they get up high that we get nice, stable, straight line directions. So after we've done all these tests and measured all these samples, then we can sort of average for the different flows. And then we need to plot that data somehow. So remember, we were looking at vectors, field vectors on the surface of a sphere. But that's sort of hard to plot. So what we like to do is fold those vectors on a sphere down onto a flat plane, like the equatorial plane. And so what we do is we project, we have the declination angle going around the outside, and we have the inclination coming from 0 to 90 at the inside. So in South America, the normal directions plot right here. They're pointing north, and they have inclinations of about 40 degrees. They're open because that indicates that the vector was pointing up. The reverse directions for South America are down here. They are solid because the vector there is pointing down and towards the south. And here's where all our transitional data falls. At first you think, well, it's pointing south, but it's pointing in the wrong direction. It's pointing up rather than down. So we know already that there's something funny going on here. Now, what we can do is think about the pole of the Earth that caused these fields. And if you're just a nice normal field on these young rocks, you could use this, and using spherical geometry, you could calculate where is the pole that gave me that direction. And for young rocks, it better be pretty close to the North Pole. And the same we could do for the reverse rocks. And we also can do it for these rocks and see where would be the pole that would give us that direction. And so that's what's plotted here, the poles that have been calculated for those different directions. So the reverse directions are down here on Antarctica, giving you a south pole. The normal directions are up here. Some of them are over on the back side there, giving you the North Pole. But all that transitional data falls right in here over Australia. So this is where the field was pointing when the reversal was occurring. At the same time, as we were doing all this paleomagnetic work, they were doing the geochronology. And this was done by Brad Singer, who's at the University of Wisconsin now, and runs a geochronology lab there. So the geochronology takes a lot more work and a lot more detail, which means they don't do so many samples. But he does have 5 samples from the QTW-10, and he has 6 samples from QTW-11, and averaged together, they give you an age of the reversal of 792,000, plus or minus 3,000 years. So when we finished this work, we came up with these conclusions for Totara San Pedro. We have 2 sections representing 26 lava flows that give us transitional directions. And you don't know this yet, but you'll see it in another slide. That's about 5 times more than other people had at that time in terms of these transitional directions. We also have the pole positions for the transitional directions clustering over Australia. And we have an age for this of 792 plus or minus 3 kiloyears. So now what we want to do is compare this to what other data we have from lava flows. And we have a few other things that have been published. So we'll look at other transitional flows. So here we are plotting the poles again. So you can see the red Chile sitting right there. In green, we have Tahiti. And this was a study that was done before our work, but it's the one that suggested that maybe there was a preferred path. And the people who did this, these results said, hey, it looks like it wants to go up through East Asia. And you can see it's very close to where we have for Chile. And it looks very simple. It just went reversed, sit here, go normal. But then a record came in from Hawaii, from Maui, and that's shown in blue. And that one is a bit more interesting in that it starts down here, it moves up through South America and into North America, and you think, oh, it's there, it's normal. But oh no, it turns around and comes back down, way down into the southern Pacific, and then back north again. Has a much more complicated path. And we'll see in a minute it has other complications. And then we have some yellow stars from La Palma, which is in the Canary Islands. The problem with La Palma is that although these lava flows were all pretty close together, they were not in stratigraphic order. They did not lie one on top of the other. They were separated, the outcrops, so you couldn't tell which one was where. So you couldn't draw lines through them directly, but you knew you had some reversed, and then you had some that were transitional, and then you had a normal. So this is the pattern that we had. We then looked at dates of all of these, and in fact, Brad Singer redated all of these so that all the dates would have come out of the same laboratory. And the dates that came out of here, just this is age across here, so we're going from 840 to 740,000 years ago. And here's the Chile data, all very consistent right here. Here's the La Palma data, sitting right in here. And there's the Tahiti data. And when we first published the Chile data, we said, oh, this is a lovely reversal. It starts down and reversed. It moves to Australia. It sits there a little while. And then, bam-o, it goes normal. Nice and simple, relatively fast, great. And it looks like Tahiti and La Palma might agree with that. But then the Maui dates came in. And Maui is much younger. Even though it has that complicated path, it would have been nice if part of that path had been older, part of it had been younger, but it is much younger. And then there's a far more serious complication, and that is that another way you can date when the reversal occurred is to use astronomically tuned ages from marine sections or ice cores, where you're tuning to variations such as precession, of which are external to the Earth, but you can relate them to the sections. And when they do that, they find an age of about 780 for the Bruns-Machiyama, which agrees very closely with the Maui data. So what's happened right now is we have a bit of a controversy going on about what's going on. Our latest interpretation of the Chile data is that it represents a precursor or a beginning activity of this reversal, and that reversals may be much more complicated than we had hoped. That they may start reversed, go all the way up to normal, and then go back to reversed again for a little bit, and then go back to normal. So that we're catching in these three, Tahiti, Chile, and La Palma, we're catching this first waffle back and forth, and then in Hawaii, we're getting a second waffle that's actually quite complicated. So this is where we are now, and the age people are fighting out what they think about this. There's a paper in press right now that's really complicating things because this group is saying, oh, we think it's 800 kiloyears old. And I'm not really in the age dating group. I just supply them samples. So I'm waiting to see how they work this out. So we have a picture now of the Bruns-Machiyama reversal that is more complicated than we initially thought. Indicates that the field varies back and forth quite a bit during the reversal time. And now what I'd like to say a little bit about is, are we heading towards another reversal? And if you paid any attention to some of the hoopla about 2012 and the things that were supposed to happen in 2012, you have to be a good internet reader to get into this. But one of the things that was supposed to happen in 2012 was there was going to be a reversal of the magnetic field. And a few quotations, I'm not going to read all of these to you, but from some of the blogs there, that we were all going to mutate into zombies, or it was going to knock out all our satellites, global economy was going to collapse, the North and South Pole would face east and west, and that was from some website that had a lot of other things going on too. But even so, a little bit more reliable, that we were going to have chaos causing life-alternating flip of the magnetic field. So we need to talk a little bit about what is this big hoopla about the magnetic field reversing and how much should we worry about it. And the reason that people get concerned about it is shown in this diagram, which is actually a painting and not to scale. obviously. So here's the sun out here, and emanating from the sun, of course, are a large number of charged particles, cosmic rays, being borne away on the solar winds. And here's little planet Earth, but our magnetic field essentially makes a magnetosheath, or a boundary, which can warp those solar winds around us so that we don't get directly bombarded by the cosmic rays. Now, some of them do make it in, and if you've seen the northern lights at any time, then you're looking at the results of these cosmic rays coming down, particularly around the field lines in the north and south polar regions. So one of the problems is if the field reverses, and what might be happening if the field dies away and gets weaker, then what's going to happen to this magnetosheath here? And are we, during a reversal, going to be bombarded with a lot of evil cosmic rays? And then suggestions that maybe there would be mass extinctions or problems, mutations, etc. So to look at this, I don't think there are any scientists who have any worry about this at this point. There's absolutely no correlations found between magnetic reversals and extinctions. There are lots and lots and lots of magnetic reversals, and you saw them on that time scale. We have them all the time, and many more than the extinction events. Now, every once in a while, just by serendipity, there is a reversal at the same time as there might be an extinction, but it's never been shown to be the cause, and we have lots of reversals with no extinctions. The rate of change in the Earth's field is relatively slow relative to biological changes, and even if the field does die down some, the atmosphere persists for a while, probably long enough for the field to then increase in the other direction. So we don't see that there's going to be a lot of problem when the reversal actually happens. And even more importantly is the duration of the reversal. You're not going to wake up tomorrow morning and suddenly have your compass pointing south. The estimates of how long it takes ranges from about 7,000 to 20,000 years. So this is not something that is going to affect us in the short term. There have been a few instances when there's been pretty quick movements of the field, but these have been over relatively small areas. And even if those did occur, they would not influence greatly. The other thing that some people bring up is that the intensity of the field is going down now. People who measure the intensity continually, it is decreasing. And they say, oh, it's going to go to 0. Well, if it continues at the rate it goes, it'll take it about 2,000 years to go to 0. So we won't be around to see it, but we don't know whether maybe it's just increasing or decreasing over time. So here's a plot of the dipole moment of the Earth on the vertical axis here over time, and here's where the reversal was back here, and we're going forward in time to the present day right here. And you can see how this dipole moment has bounced up and down. And here we are right here, right now. It's actually pretty high for what it's been in the past many times. And so even if it is going down, it may go down and up again, down and up again. So we don't see that the fact, because it's reversing right now, is going to mean that we're going into a reversal at this point. And finally, I just want to say that from studying reversals, and this reversal that I looked at, we know quite a bit more about what happens with a reversal, although, as so common in science, we haven't really solved all the problems. And we've created a few more. The reversal does seem to be more complicated than we expected at first view. And so this just means it gives students and other professors more things to do in terms of hoping to find their needle in a haystack. And finally, I'd like to say a few thanks, as you always do when you get these opportunities. I first want to thank my family. My husband and my daughter are both geologists. My son is not a geologist, but that keeps the rest of us not quite so rock-loving as we could be. Thank them for all the support When you have a mom who goes out in the field for 3 months at a time, it can be interesting. I also want to thank my department. And as Steve said, we're one of the most congenial departments on campus. Every year we take a picture on April Fool's Day. And here we are a few years ago. Of course, there are no fools in that picture. And we use this on a calendar that we send out to our alums. But this is a great department to have worked in. I've been here 38 years. It's just a wonderful family and very, very supportive, everybody in it. I particularly want to thank Mark Leckie, who is our department head and is noticeably absent today. And we got our signals a little crossed last September when we were scheduling this, and it turns out he is running an international meeting in Houston this week, so could not be here. But I want to very much thank him because he's the person who nominated me for this award and put together the nomination. And I also wanted to mention 2 of my graduate students. I talked a little bit about Jim, who was there on the trip. Jim now works in the Netherlands for Shell Oil Company. But 2 other graduate students have been really influential, and actually Steve mentioned both of them. There's Susan Solianis, who was my first graduate student, and she also was the youngest PhD we ever have awarded. And she was a terrific way to get started when I first was at UMass. And then my student Suzanne McEnroe, who was a little later on, but with whom I've become very good colleagues. We spend a lot of work together, and she has lots of plans for what I'll do when I retire. So that's going to keep me young forever. And finally, the very last thing I'd like to say is I'd like to echo what Tom Zoller said last week, 2 weeks ago after his chancellor's talk. And that is that it's been a wonderful gift to be working at a place like UMass, a research university where people are very, very supportive and encouraging, and you're able to go off and do these wonderful projects. So thank you very much.
Wonderful talk. That was really stimulating. I'm sure there are many questions, and Professor Brown's gracious enough to take some from you. So please, who would like to start here?
Do I understand that the thought is that you don't have to have much change in the currents in the core in order to produce a flip like this?
Right, yes. He's asking about the currents in the core. You don't have to change their direction or make any big changes in them at all. And they feel that there's some just very little instabilities can be enough to switch the signal. Yeah. Yes?
Is there any instances of these actually slowing down? It's like the core cooling, any of that having any effect?
Well, the core is slowly cooling. And eventually, but it'll be a long time in the future, if that outer core completely cools and solidifies, then we would no longer have a magnetic field. But that is way, way off in the future. But the size of the field seems to have been pretty consistent over time. Yeah. Yes?
You said that there were some quick reversals, but they were over small areas?
Well, yeah, it wasn't a whole reversal. It's just some people have found, well, 2 people actually, it's only been found twice, have found one lava flow where in the bottom of the lava flow you get one direction, and in the upper part of the lava flow you get another direction that may be 20 or 30 degrees difference. So some movement over the time in which that lava flow cooled. But they've never seen a whole reversal in that time, yeah. Yeah.
I was fortunate enough to study and be in the same institution as a couple of the guys you mentioned there, Rob Coe and Gary Glassmeyer.
Yeah.
Gary makes that modeling seem so easy, but he has, 19 equations of state or something that are part of it. But one of the things that we sort of, as graduate students around him, came to know is that it's really impressive that he was able to simulate the magnetic reversals because the time scale is so different. There's some that stay one polarity for such a long time, and then the others that switch very quickly. And he managed to simulate that in the model. I wondered if you could comment on why that's such a Herculean modeling feat to get that right.
Well, the first problem is there are all these different equations that you have to use. You know, there are 4 Maxwell's equations, and there's this equation, there's that, a whole number of Stokes' law, whole number of equations. The other problem is they all have a number of unknowns. They also all have some values which you must assume values for. And we just don't know enough about the outer core to be able to have good, I mean, some of them, the numbers they put in there, an order of magnitude works, you know. So it's just a huge problem. And he was the first one
So
to
is he
actually.
good or lucky?
Well, I think he's both. I think he was really good. He was really good, but also they were pretty lucky. And they actually did see this reversal in the unfolding of the equations, and I think the second or third try they had at it. So it was pretty impressive. Yes. Oh.
Could,
Sorry.
if a solar flare that's strong enough actually cause a reversal of the polarities?
No, the solar flares, the worry about the solar flare, if you had a huge solar flare, it could maybe influence things like satellite transmission and that kind of stuff. And there have been some instances, you know, I think one big solar flare caused a problem up in Quebec in terms of the power system and stuff. But it doesn't seem that they have any relationship to changing the field. It's all internal. Yeah.
Could a solar flare have any ability to like help trigger it if there's?
Well, I don't think so, because the solar flare, I think of the solar flare is out on the surface. It's in the atmosphere and coming down. And all of the rest of this is deep, you know, deep in the earth, and motions and things that are going on down there. So to get something on the surface to affect that is pretty difficult. Yeah. Yes?
I've forgotten the Spanish name, but did you have to worry at your site about kissing bugs?
We didn't. I'm afraid I'm not familiar with kissing bugs. We had very few problems in the field in terms of you know, natural enemies of any kind. It sort of was a great place to work because there were no bugs and no snakes, no little critters to eat your food, no big critters to eat your food, you know, so it's pretty ideal. Yeah, I think Maxine, yeah.
I'm a micropaleontologist from a quarter century ago in that department, and when I was there, another graduate student, Peggy Shannon, and I were talking about, I think it was Dean Goodwin's, there was something about soil bacteria that had magnetite.
Sure, so it
And
turns
we had
out
this
that
big exciting thing. We thought we could do a project together, and I wonder if you guys ever talked.
Never.
all the time. I just say one thing about the magnetic type of bacteria. So it turns out that there are bacteria that orient themselves in sediments along those same lines of polarity. And those bacteria were discovered here at the University of Massachusetts in the microbiology department. So
Yeah, the story I always heard is they were found in the campus pond.
Sue probably knows. Were you here at that time, Sue?
Yeah, I came right after that was discovered. Actually, it was an undergraduate who discovered them, quite by accident, by putting a magnet, looking through the microscope, putting a magnet up
To
next
the-
just randomly, and said, wow, look at that. Then did an experiment, put the magnet on the other side. Wow, they're going the other way. And the graduate student was Dick Blakemore.
Yeah.
He said, get out of here, let me see this.
Took it over. Okay, yeah, one more.
You mentioned these minute instabilities that cause these reversals, right? Could you please elaborate a little bit more?
Well, if you look at all the equations that are, you know, governing the magnetic field, and this theoretical model that people have worked on, it seems just as the equations are unfolding that something, they don't even know what the instability is yet, or have a way to indicate it. It obviously has to be something that's pretty common because we have so many reversals. But, I mean, see, poor Steve, when he had Geo 101, didn't get the idea of what causes reversals, and we're really not a whole lot closer now.
There's nonlinear equations or what?
Yeah, yes, yeah, very complicated. Yeah.
Well, let's thank her again for a wonderful talk. I appreciated Dr. Brown's emphasis. I appreciated her emphasis on her luck in finding this site, and I think I speak for all of us to say that we're very lucky to have heard the talk and also to claim her as a colleague. And it's now time to introduce the Chancellor, who will present the Chancellor's Medal.
So Professor Brown talked about the fact that the NSF waits until you find the needle in the stack and then gives you money. We wait until professors completely show their full worth and inspire us for 38 years before we recognize them as well. And with that, I'm very proud on behalf of the entire faculty of this campus to give you the Chancellor's Medal, which recognizes both the inspiration you provide us and the pride that we take in your accomplishments. Thank you.
Thank you very much.